So Billy said there's an Easter egg when I attach a speaker, so don't clear the boards.
Oh.
Something's supposed to happen. Let's have a look.
All right.
What?
Auto clear?
Oh,
look at that.
Look in the sky.
Oh my God.
Oh, man.
Wow.
Oh, that's so awesome.
That's awesome. That is cool.
Oh, thanks, Billy. That's fantastic.
Wow. Nice.
How did he manage? Yeah, those are really big parts up in the sky. I'm going to take the camera up and have a look. Oh, yeah, I see.
Yeah.
Wow.
It was a projection of the first board.
Yeah, it's wrapped into a kind of dome that's up in the sky. Oh, very cool. All right. Cool. And there's something else over there in between the board set. I guess we'll get to that in a minute. But oh, cool. It got cleared. Oh, so I'm actually going to write in the sky when I do this proposition.
Oh.
It used to be like that, remember? Right. We had for a while.
Yeah. So that's right. Yeah, right.
Billy has restored that, but better. Okay, so we did Proposition 8, Book 3 last time. Proposition 9 is just another characterization of the center of a circle. So what it says is, if a point be taken within a circle, and more than two equal lines fall from the point on the circle, then that point is the center. Okay, the proof's pretty easy. So suppose given a circle, suppose given a point, D, and suppose that we have at least 3 lines from that point to the circle which are of equal length, and I'll call them A, B, and C. So suppose AB, sorry, no, suppose DA, DB, DC are equal. We aim to prove that D is the center. Okay, well, let AB and BC be joined. And drawn through, and bisected at EF. I won't cite the proposition, we've done this enough times. So bisect at E and F and then draw lines through. Through those bisecting points to K and L. All right. So now let's see what we can say about that. So I'm not going to write down this argument because we've done it many times. Since we've bisected this line, right, AE and EB are equal, and the side ED is common. So we know, we've done this many times, that these are both right angles. Okay, so that means if we extend DL to H and KD to G, this is H, this is G, then GK cuts AB into equal parts and at right angles. And that should ring a bell, because one of the first results we proved in this book was to do with this situation. So the center of the circle is on GK. That was book 3, proposition. Oh, it wasn't just early, it was the very first one. For the same reason, the center is on HL. So we have two straight lines, distinct straight lines. Why are they distinct? Well, because A, B, and C are distinct points. So you can easily argue from that K and L are distinct points, and therefore these lines are distinct. So since two distinct lines meet at most one point, this I'll comment on. D is the center. Because the center is on both of those lines, D is by construction on both of those lines, and therefore the center must in fact be D. How do we know that two distinct lines meet at most one point? Well, that has to depend on the parallel postulate, because it's not true on the sphere, say. I don't remember actually stating this in that way and proving it, but it follows from some of the things we did in book 1. Do you remember actually proving this? I mean, I came up with the proof, but I couldn't remember actually. I looked briefly and couldn't find it.
I don't remember proving this. Yeah, I didn't do it. Or maybe I didn't, I forgot.
Yeah. So if I can't find it, maybe I'll do the proof next time. But yeah, this follows, you have to use the parallel postulate somewhere. Okay, that's it.
Oh, I have some vague recollection of you doing it. So it's probably in the backlog history somewhere.
Yeah, I'll take a look.
Cool. So that's the method of proof here is going to be used again in proposition 10.
Yeah.
Oh, so when you disconnect, the sky clears and becomes day again.
That's interesting.
All right. So I'm gonna connect.
Yeah.
Speaker, and then I guess the sky will darken again. Nice. What if I start writing on the next board though? I'm curious. I have to try this out. So I walk along. Oh, so it's only board 1?
I don't know. Try it. Yeah, maybe. Yeah, try writing. Oh, no, it's not coming up. Try disconnecting as speaker and then reconnecting. No,
No, so it's stuck on board one.
Just board one. Oh, that's okay.
So I'm not going to have the cool effects of drawing and have the fill up because Dan takes that honor.
Yeah.
No worries. Cool. So I think we have enough time to do the next one, which is as I said, the method of proof is similar, but I think what we're proving is a little different. So proposition 310. So the proposition here says that a circle does not intersect or cut another circle at more than 2 points. So a circle does not cut another circle at more than 2 points. So that the diagram here is interesting because it assumes that there are 4 points of intersection. So I don't know if we right. So I guess I don't have a proof for there being between exactly 2 or 4 points, right? But this will rule out anything greater than or equal to 4 points of intersection. We can think about whether something like this can be made to work for 3 points a little bit afterwards. So I'm going to draw. I'm actually going to draw some ellipses because that's the only way to make the diagram work. So these are meant to be circles, but I'm going to draw eggs. And as I said, this we're going to assume, right? Kind of assume that they intersect at 4 points, right? And so we're going to call them B, G, F, H. Again, the reason why these are not what letters you expect is because I'm following Euclid's text. Okay, so all right, so we're going to assume that they intersect at 4 points and then construct some lines. And these lines are just going to be the ones that connect these. You don't have to connect all of them up, just some of them. So I'm going to connect B and H like this. I'm going to connect B and G like this. And the construction we're going to make here is we're going to bisect these lines. So we're going to put a point on these lines, which is the midpoint, with previous proposition allows us to do this. I actually don't remember the number. They didn't reference it. I didn't look it up, but we can bisect these lines. Right, like this. And then we're going to construct perpendiculars from on this point. So I'm going to call this point D, and this other point, which is the midpoint of BGL. We're still not getting kind of letters of the alphabet that line up. But anyway, that's what they are. And we're going to construct perpendiculars like this. This, and another one going from here, cutting this other line, right? And these are going to be right angles, right? And so the proposition that allows us to do this was referenced. So I can say proposition 1.11, right? Construct perpendiculars or lines, constructs a line at right angles to a given one line at a point. Okay, so that gives us these lines, and we're going to call the intersection P, right? And you can probably guess what I'm going to do. I'm going to say that P is the center of both these circles, and then invoke another proposition that tells us that that's not possible. Cool. So that's the construction. Prove I'll move along a little bit to the next board. Oh, maybe I don't need to. I'll just go to the next board. So the proof. So by proposition 3.1, the corollary to proposition 3.1. Remember, 3.1 was the one that allows us to identify, construct, find the center of a circle. But the corollary tells us that the center of the circle is actually on, I guess, in the picture, is on the line PD, right? If you look at the line HB, so the construction goes, right? This construction of bisecting a line, constructing the perpendicular was something that we did in 3.1, and so yeah,
center finding algorithm.
Right. So the algorithm tells us that if you follow that algorithm tells us the center of. I'm not going to label the circles. I'm just going to say the first circle.
Which is which one?
Which is, I guess, pick one and stick with it. I'll just say.
Kenneth's proof is invariant to your choice.
Circle. With it, the first circle, the one that's labeled green. I guess, yeah, it doesn't matter, right? The first circle is on the line PK.
Yeah.
Right. And so, of course, similarly.
You didn't actually put the K on there. But...
Oh, I didn't. Oh, my God. I'm sorry. So that D is meant to be a K because that doesn't make sense. Why would I put L and K? Sorry. Let's change that back to a K. We don't need that many letters, right? Euclid labels a lot more points, but we just need these ones.
Yeah.
Okay, thanks, Dan. PK. Similarly, PL, right? So we can apply the same argument to the other line, BG, right? It's completely symmetric. So the center of the circle is also on line PL.
Well,
right?
I think the way you've written it is, it's the center of the line, not PK, but the extension of that line to.
Yeah. That's true. Right.
So I think Euclid's right to put in more letters.
Wait, but isn't the center P? Oh, they might not intersect at P. Well,
no. Just like if you say PL, that means the line segment from P to L.
That's true. It's still true though, right?
No, it's not the center of that line segment.
The center of the circle is on the line.
Once you've bisected, so you take BG, you bisect it, you erect a vertical line from L,
right.
And then the center of the circle is the center of that line when you extend it all the way from from the circumference of the circle through to the circumference. That is the center. But
yes.
P is just at the moment the point of intersection, right?
Oh, yeah. So, okay, a line. Yeah, okay, maybe that's why they had more letters there.
Ken is like this stingy bastard with the letters and doesn't want to label all the time.
This is probably because I'm going to blame this on like programming and any unused variables. I'm like get yelled at, right? I shouldn't have them, so I just get rid of them, right? No, I'm trying to be parsimonious for the letters I'm using. Anyway, extended. How do I say this? Extended.
Just put in the letters, man. I'm looking at the diagram. Just put in A and C and M and E.
Yeah. A, C. No, so like I have them. So it's all good. I didn't want to put in the wrong letters.
Well, you just did. What I mean? That's not D.
Okay, so I labeled some of these C, D, E, and M, and they intersect. Well, okay, so that's fine.
Yeah, I'm going to move your K though, because it looks like it's that point where the line meets the circle, but that isn't what you mean. You mean K.
Yes.
Yeah. All right, cool.
Okay. So, DC. Right, and similarly, yeah, the other one is ME, I guess.
Yeah.
ME, right? And so, by the similar argument as previously, the center of the first circle is P, right? Which is the intersection of ME and DC. Okay.
Wait, what?
And
I didn't follow that. So we know the center is the midpoint of ME and the midpoint of DC. But why is that? Oh, but it has to be on both lines, and for the same reason.
Yeah,
as we
be on
just
both
explained.
lines.
Yeah. Okay. Yeah. Mhm. Yep.
So this applies also to the second circle, right? So this, because it, those points that we picked, B, G, F, and H, they're actually on both circles, right? So it didn't matter which circle we picked. So the same argument applies to the second circle, right? Hence, they have the same center.
Mm-hmm. Yeah.
Okay, so by corollary, proposition 3.5 tells us that this contradicts proposition 3.5, right? So this contradicts proposition 3.5, which says that if two circles touch or cut each other, they cannot have the same center.
Well, you didn't need 4 points. I don't know what you were worrying about earlier. You just needed 3, right? So that
I just needed 3?
You only needed...
Oh, you're right. Yeah. I didn't use F.
Yeah.
All right, there you go. If two circles... I threw them in. I thought I used it. I guess I could have not labeled F, right?
Yeah, Euclid just wanted to avoid some grotesque diagram that looked even worse, where it only met at 3 points.
It tricked me. Totally thought I needed F, but I didn't. Okay, I guess I contradicted myself. I was trying to be parsimonious with variables I needed, but I left the one that I didn't use.
That's right.
Or touch, then we cannot have the same. Then cannot have the same center. Okay, so that's it. That's the proof that if two circles touch, if two circles cut each other more than 2 points, then they circle does not cut.
Speed.
Yeah. Okay. Yeah, the other way around. More than 2 points, then they cannot be this. They can't be this. They can't have the same center.
Yeah. Awesome. Well, that was perfect timing. Nice work.
Cool. Yeah.
Wow.
And the sky clears. Yes. Oh man, that is super cool.
That's so epic. Yeah.
Yeah.
All right. Thanks, Ken. Thanks, Jed.